It's a particular pleasure to talk about the bootstrap. In fact, I didn't really expect to be the first speaker to talk about the bootstrap here, but so I'll have to catch up a little bit. So I'm going to talk about some work I've been doing, and initially mostly with Misha Isachenkov. There's a very short paper out, and in fact a longer is in preparation. While I was sitting here, I could see on the Dropbox that the file was constantly uploaded, so hopefully there will be some longer text coming out very soon. I'll also have, there's maybe some time to talk about some ongoing work that we are doing now with Jenya Sobko, who is actually here in the audience. So at this meeting, I guess I hardly have to motivate people to be interested in conformal field theory. Maybe one thing I would still like to say is that in addition to n equals 4 super Yang-Mills theory, there are actually lots of interesting conformal field theories out there that appear in nature in various contexts, and phase transitions, and describing the low energy physics of many interesting quantum field theories. There's of course the famous critical Ising model, more general Wilson-Fisher fixed point that you really see sort of in materials that you can produce in the lab. There's also famous non-supersymmetric Bang-Sachs fixed points in the conformal window of QCD-like theories. And of course, then there's lots of supersymmetric theories, some of that we saw also this week. And that includes, of course, n equals 4 super Yang-Mills. And n equals 4 super Yang-Mills, of course, is a beautiful theory because it allows us to try out many different alternative approaches to quantum field theory. And we have so much data now that it's probably the best toy model one could think of. Now, I think one of the very, very successful alternative approaches to thinking about quantum field theory is actually now more than 40 years old, and that's this conformal bootstrap. And so it was mostly formulated as a sort of strategy to some new non-perturbative approach to quantum field theory in the early 70s. And it relies mostly on the dissection of the symmetries and the dynamical content of the theory. That's very much like in atomic physics, where you see Wigner kind of taught people how to take all the quantities apart when you have rotational symmetry, right? So lots of quantities have tensor indices, but all these quantities carrying tensor indices, they are determined entirely by the symmetry. So you can compute them once and for all, and the dynamical content sits only in index-free reduced matrix elements. And so somehow that is of course a much simpler representation of the dynamical content of the theory. And of course, again, in quantum mechanics, that was beautifully realized through the work of Wigner. Now, in conformal field theory, the situation is actually somewhat similar. In fact, there the role of these quantities that in tensors is played by conformal blocks. So conformal blocks are objects that depend on indices, and in this case, conformal symmetry, of course, acts on the space-time variable. So the indices are basically the space-time coordinates, the index-free reduced matrix elements that contain all the dynamics, they are coordinate-independent quantities, essentially the OPE coefficients, okay? And so what you do is you dissect, or you take these two things apart. You, in principle, should first do a theory of the tensors and then a theory of the coordinate-independent part, the dynamical content. And that's more or less what this bootstrap is based upon. There's a famous equation that I'll review in a moment, crossing symmetry. And that's the equation that allows you to solve for the dynamical content with coefficients that are entirely kinematically determined. Now, what's so beautiful about this, in some sense, is that it reduces the problem of constructing a quantum field theory, conformal quantum field theory, to a problem in the theory of special functions. Okay? Now, I know that the theory of special functions is usually not very popular. Everybody seems to think of the end of the 19th century mathematics, but in fact, it's a very active field, and there's a lot of very modern theory of special functions. And in fact, this modern theory of special functions is basically integrability. To a large extent, that sort of comes out of integrability, and I'll try to show you that. So, in fact, a huge part of modern theory of special function actually originates from work of Calogero, Sutherland, and Moser, which I will partly review. So this is particular quantum mechanics problems. I mean, particles moving in a potential with some interaction which are integrable. And that has led to very interesting recent work over the last 40 years on special function that goes far beyond what was known at the end of the 19th century. Incidentally, it's kind of interesting to note that these models were introduced roughly around the same time as the bootstrap was formulated. You see, when you look at the years of the papers, which I displayed, if you remember from the bootstrap, that was about the same time. But of course, these were completely independent developments. And so what Misha and I observed, sort of published early this year, is sort of that there was that these things are actually deeply connected. And in fact, that these conformal blocks that we talked about, that I talked about in the previous slide, these building blocks, the invariant tensors of a conformal field theory, that these are actually turn out to be wave functions of some quantum mechanics Schrödinger problems, namely of a certain type of Calogero-Sutherland models. Okay, so so this is what I want to show you. Let me briefly go through the outline. As I said, since nobody has talked about Conformal Bootstrap yet, I'll have a little task to give you a 10-minute summary of what this is about, in case you haven't seen it. Then in the second part, I will turn to these quantum mechanics problems. So it's essentially a problem of studying particles on a one-dimensional line with some interaction. I'll show you a little bit of that theory and then also connect it to the first part of the story of these conformal blocks. So then in the third part, so this is just an observation on the relation of two quantities. I'll have to show you that this is actually useful for something, and so we will actually talk about the integrability. So this is basically where the subject of this series comes in. We will talk about integrability and what you can actually do with the integrability. So integrability comes into the Calogero-Sutherland models, which are known to be integrable for a long time. And they have really very useful consequences for the theory of conformal blocks. And I'll show you a little bit of that before I conclude with further directions, giving you a few more ideas what's out there. And in fact, there's a lot of stuff to do. Okay, so that is the outline. Are there any questions at this point? Okay, so let me briefly summarize on a few slides what Conformal Bootstrap is about and substantiate the statement that it's more or less brings the solution of conformal field theories down to a problem in the theory of special functions. Now on this slide, I think there's hardly anything on there that you don't know. I'm fairly confident about that. So you know conformal symmetry allows you to move any 3 points in any dimension to 0, then 1 times the identity in the x direction, let's say, 1 direction in infinity. So that means that 2-point functions are entirely fixed up to the conformal weights. And 3-point functions are entirely fixed except for this OPE, or the 3-point coupling lambda 1, 2, 3 that we talked a lot about this week, in particular in n equals 4. Now I displayed here only the 3-point function for 3 scalar fields. You can also write down a 3-point function for 2 scalars and a symmetric traceless tensor field, which is the most general type of 3-point function. Where if you have 2 scalars, the third field can be in general in a symmetric traceless tensor representation. And it looks kind of a little more complicated, but it's still true that there's only one constant that is undetermined by conformal symmetry. And this constant now depends, of course, on the conformal weight of this third field and on the spin, the number of indices of the symmetric traceless tensor that appears. So this is up to 3-point function. Now, when you want to look at 4-point function, it turns out that this 4-point function is also partly constrained by this conformal symmetry. The reason is that if you have used your conformal transformation to put these 3 points at 0 and then at 1, in the one direction in infinity, then you still have rotation around this one axis as symmetries. You can use that to bring the fourth point in the plane of the 1, 2 coordinate system. And so you only need basically two real or one complex coordinate, z bar, in order to describe what is not determined by conformal symmetry in the 4-point function. So I'm looking at 4-point function of scalar fields here. So that means basically if you have any 4-point function of a scalar field up to some simple prefactor that takes care of the transformation law, which you can write down explicitly, is just determined by the function of z and z bar. And z and z bar are these related to the cross ratios to these formulas. So you see in these as capital U and capital V in Leonardo's talk, and I parameterize them now. Instead of U, I use z bar, and instead of V, I use 1 minus z bar, which is the standard way of parameterizing. So when you see z and z bar here, you should not think of two dimensions. This is true in any dimension. You have these two parameters. And so now comes this first step. I told you that somehow the conformal bootstrap relies on the idea that you split dynamical content and kinematic content of the theory. And that's done in the so-called conformal partial wave expansions, where you take this function gzz, which of course now contains dynamics and sort of information about the kinematics, and you decompose that in a series or in a sum of kinematically determined conformal blocks that describe sort of basically exchange of one particular intermediate tensor field, and then these 3-point couplings or OPE coefficients. Okay, so these conformal blocks here, these are sort of entirely kinematically determined. These are really objects like the tensors in atomic physics that are determined by just SU2 group theory. So there's various ways to kind of construct these things or think about them, but sort of the easiest way to state is to understand them as solutions of a second-order differential equation that comes essentially from just expressing the fact that what these things are is basically describing the exchange of a single irreducible representation in the intermediate channel, which is described by the conformal weight delta and L. And so there's a particular second-order differential operator that I describe here, whose such that these G functions, which are really these G functions G of delta L, the conformal blocks that appeared on the right-hand side of the conformal partial wave expansion, are eigenfunctions of this second-order differential operator. And so the precise form you can work out. I mean, it was worked out by Dolan and Osborne more than 10 years ago. And so this is what it looks like. So it's a second-order differential operator. And so let's start. Remember, these G's are a function of Z and Z bar. So it's a differential operator acting on Z and Z bar. And so there's a piece that acts on Z only, like this. It contains two constants A and B. These A and B have to do with the data of your external field. So we are looking at 4-point function of 4 scalar fields. Of course, they have conformal weights, right? I call them delta 1 to delta 4. And then from these, I can build the parameter A and B. And these parameters A and B, which are determined by the external fields that I put in, and their anomalous dimensional scaling weights, determine this particular piece of the operator. So there's one guy like this differential operator here. Then there's another differential operator which depends on Z bar and acts only on Z bar derivative, a coordinate. And then there's another piece which is mixed. You see here you don't split into Z and Z bar. It contains both Z and Z bar. Coefficient in front of this is epsilon, which is D minus 2. And D is the dimension of the theory you're studying. So you see, when you do this in 2 dimensions, this coefficient here is 0. So this ugly piece here disappears. And you just have a piece that acts only on Z and a piece that acts only on Z bar. And that, of course, is this famous sort of splitting into left and right movers in 2 dimensions that makes 2 dimensions so special. But in general, there's this interacting piece that couples left and right movers. So the statement is basically if you solve these second-order differential equation with some appropriate boundary conditions, which I don't want to specify in detail, but they're well understood, then you get these conformal blocks. Okay? And of course, we'll talk more about this. So remember, we needed these conformal blocks to write down this conformal partial wave expansion that I had on the previous slide. So that was the kinematical content, and the coefficients were just the OPE coefficient, the dynamical content of the theory. So let me just go back to that. So here I symbolically wrote the same equation. So here's the 4-point function containing the kinematic black information and the pink dynamic information. It's split here into these conformal blocks that we discussed on the previous transparency, and the dynamical content, these OPE coefficients. Now I personally like to write this side through an integral. This basically, I take these conformal blocks here and these products of OPE coefficients I call a P of lambda, P of chi. Chi is basically delta and L. And then I write it as an integral. And you should think of this as basically you evaluate this integral by picking up pole contributions. And that's how you get the sum back. So these P functions here contain poles at places, at dimensions where the fields sit in your theory. Okay, so the pole positions of P contain the spectrum, and the residues contain the information about the OPEs. And then there's actually an integral missing here. Now we come to this famous crossing symmetry. As you all know, this is basically, we've done this now in one particular channel, the S channel. We can also do the same conformal partial wave expansion in the T channel. We get a very similar formula, but with a different set of conformal blocks, which can also be found. And crossing symmetry says that the 4-point function, physical 4-point function, of course, has to be independent of how we performed this computation, how we decomposed into the dynamic kinematical content. And then it's actually very nice to multiply this with, or take the scalar product with the S-channel conformal blocks here and write this really as an equation, as an integral equation for the dynamical content, the pink stuff, in terms of the kinematical content. Okay? So the way I want you to think about this is now, this is an integral equation, and the dynamical content, the kinematic content of the theory, this overlap of these blocks that we discussed on the previous slide, they provide some kind of integral kernel, okay? And the dynamical content is basically an invariant under an integral transformation, okay? Like when you take a Fourier transform, the Gauss curve would be such a function. So somehow it's a generalization of that, this equation. So, so that tells you, in order to write down this equation, of course, you have to know in particular what this kernel is, okay? And now, could you make you guess what this kernel function will be? That's what one is after. I mean, this was just a picture, but of course, it has to be a function of the spins, L and L prime, and of the dimension, and it will have some kind of complicated dependence on these L and L prime and delta prime. And you can start guessing what this special function actually is that defines this integral transform. Okay. Now, I don't know if somebody wants them to take a guess, but it may not be so difficult to kind of argue that it should be some sort of hypergeometric function. But in fact, it is also not so difficult to argue that it should not be one of these normal hypergeometric functions that we know in one variable, but it should be at least sort of a two-variable hypergeometric function in general. And then, of course, we enter a very difficult realm of special functions, and you might recall some of you Appel functions, and maybe now turn away and think this is not really your cup of tea. Anyway, so we have to come to terms with this special function, okay? And so let's move on. So now we want to bring things a little bit closer to home, and I start now with the second part, and we'll review sort of the quantum mechanics description. So as I told you in the beginning, the theory of special function, modern theory of special function, is very much a theory of integrable Schrödinger problems. Okay, and so we'll completely change gears at this point and talk about such quantum mechanics problems. In fact, maybe. So the first problem is actually a very simple one I will discuss. It was in quantum mechanics discussed in 1933 by Peschel and Teller. And in fact, I will discuss it the other way around. So we'll come back to this Casimir equation that I showed you. So we want to understand these conformal partial waves, right? Because, again, our crossing kernel was an overlap of these things. And so I pointed out that in 2 dimensions, this mixing term here is not present, and all we have are these purely left and right moving part. And of course, we can solve now for these conformal blocks by just solving the left and right moving part and multiplying them together. So when you do this, you get just a differential equation for this left moving part, which is just half of this. So just with this d squared operator acting on a function, d squared operator again was just this second order differential operator of z with some eigenvalue. And that's the equation I put here. So that's the equation one has to solve for z bar, and then multiply. Now, there's a funny transformation one can perform. You can actually take this differential equation, take this function g that is supposed to be an eigenfunction of this differential operator d squared, depending on parameters a and b, which enter this differential operator, and you multiply that with this funny prefactor, and then you can actually check that this new function, you define a function psi of x in this way, where x is related to the z by this transformation here. And so you work, you have to just compute for a few minutes, and you will see that then this psi function, if g is an eigenfunction of this d squared operator of this form, the psi function will actually be an eigenfunction of a one-dimensional Schrödinger operator with a potential which has this form. Okay? So it is a funny-looking potential, actually quite strange looking. You have these 2 potential pieces involving sinh squared in the denominator. So the potential kind of blows up at 0, goes to infinity. So it roughly describes sort of a particle moving on the one-dimensional line with a potential in half line, because there's sort of a wall, an exponential wall at 0. Okay, so that's the type of problem. And when you first see this type of funny-looking potential, you might be scared that you cannot really write down proper eigenfunctions explicitly, but what Peschel and Teller, of course, found, they did this trick the other way around, and they mapped it to the hypergeometric differential equation, and of course that way they solved this problem. So now this is a nice quantum mechanics problem of a particle moving on a line in a potential. So what then happened in the 70s was that people looked at generalizations of this problem. So they thought, okay, what can I do? I can now start to put in more particles in my potential, okay? So I can have a second particle, third particle. And of course, as long as I just put particles in, that's a little boring. I will want to make them interact somehow. And I will look for interactions between these particles that preserve integrability of the problem, or solvability. And so mathematicians actually came up, physicists, with a scheme to classify such integrable particle Schrödinger problems. So one thing I might have should have pointed out, so this slide usually has some nice animation, which I maybe now have to do by hand. Oh, certainly this is. So when you look at the potential before for this Peschel-Teller problem, you see it has these 2 pieces, and there's a sinh squared function of x over 2 and the sinh squared function. And so in some sense you can think of this potential as being associated with a root system. Okay? So the sinh squared is a symmetric function, so you can think of a root system that looks like this. So there's 2 roots related to the sinh squared over x over 2, and 2 roots, longer roots of twice the length, related to this piece with the sinh squared. Okay? Now if you do, so this is just a kind of a way to remember this potential, and each type of root has 1 coupling constant roughly attached to it. Okay? Now if you want to put a second particle in this potential, then of course, as long as it doesn't interact, you would just do a second particle with a new coordinate, would be like that. And so now what mathematicians found is that you can actually introduce an interaction that corresponds to putting in extra terms of this type. Okay, so the potential after this, when you translate this back from my funny picture to a real formula, the potential looks like this. So it has two of these special Teller potential describing just a one-dimensional particle in the same external potential. So we have the same parameters A and B that parameterize this external potential. And then we have these two interaction terms which correspond to these, this one here to these two roots and this to these two roots. Okay? And since these are new roots which are not related by any symmetries to the old roots, there's a new coupling constant in this theory. And that's what I called epsilon here. Okay? Now, when you write down this Schrödinger problem, you can actually check that it's again an integrable Schrödinger problem. So you can solve this system. And the way you show that is that you can show that the Laplace operator that you get here is actually the sum of squares of some commuting objects. And these commuting objects are called Dunkel operators, first order operators. So in a free field theory, for free particles, this would be just d by dx. Okay, so the Laplacian is sum over d by dx squared. And for this type of problem, we have a generalization. The d by dx, of course, doesn't work. But you have an extension of this first order differential operator, a set of first order differential operator that commute. And when you take the sum of squares, you get this Schrödinger operator. Good. So this is, these are integrable Schrödinger problems. Now we have to come back to our conformal partial waves. And the statement is as simple as you could possibly imagine. So we were interested in these conformal partial waves, G delta L in a d-dimensional conformal field theory, depending on conformal weight delta and spin L. And so the claim is, and it's very easy, elementary to verify, that if you have a G that satisfies these differential equation that I showed you a few slides ago for conformal partial waves, with this complicated interaction term between left and right movers, and you apply to this multiplies with this prefactor and do the same variable transformation from z to x that we did before. Now z1, z2 are z and z bar. Then this function psi here will actually be a solution, an eigenfunction of this Calogero-Sutherland Hamiltonian with the epsilon parameter that we had in this interaction, was modeling the strength of the interaction being related to the dimension in precisely this way that epsilon is d minus 2. Okay? So in particular, yeah, so that's the statement. And this is the first statement I promised to you. So in this sense, we have now understood that these conformal partial waves, the building blocks of any conformal field theory in d dimensions, are actually more or less, by this simple transformation, they are just related to wave functions of this integrable Schrödinger Hamiltonian in two variables, describing basically two particles in one dimension interacting by some funny potential. Yes?
Could you just remind what are Z and Z bar in CFT?
So Z and Z bar in CFT, again, are related to the cross ratios. And so this one of the cross ratios that Leonardo called capital U, that is usually called small u, is ZZ bar, and the other is the V is 1 minus Z, 1 minus Z bar. Okay, and that's so it's basically just cross ratios. Is one version of parameterizing the cross ratios. Any other question? Okay, so. So I didn't really talk too much about boundary conditions, but when you kind of take them into account, then you actually see that these conformal partial waves, how they're really related to scattering states. So in this two-dimensional problem, basically when you think about it, it describes well, either two particles in a one-dimensional line or one particle in a two-dimensional strip. So let's say you have actually one particle in a two-dimensional semi-infinite strip with exponential walls. And at infinity, this potential becomes constant. And so at infinity, you can impose sort of boundary conditions. So it's an exponential wall. So you have a discrete set in this of eigenstates in this direction. They are parameterized by L. And then in the direction into this strip, you have basically continuous spectrum. And that's the parameter delta. So you impose at infinity this boundary condition that at infinity at infinity of this strip, the wave function is basically a combination of a free wave in this one direction and one of these eigenstates of this, these are just Jacobi polynomials, and then the corresponding wave function of this Calogero-Sutherland model with these boundary conditions will be the conformal partial waves. Okay, so you get a very nice interpretation of conformal blocks in terms of scattering states in this quantum mechanics problem. Okay, are there any questions? Good. So far so good. This is all fairly simple. We have now just compared two different sets of equations and we found that they agree. Maybe with this slight extra benefit that for the second description, I mean these quantum mechanics problems, Schrödinger problems, people understood a long time ago that they're actually integrable. And but so now what can we actually do with this identification? Can we actually learn something for our conformal partial waves? And that's what I'm going to discuss now. So I want to discuss what are the consequences of this integrability that sits in these problems. In fact, I think when we wrote down, I mean, this correspondence, we expected somehow that now we open math books and we just find all sorts of formulas that have been developed using integrability on these conformal blocks. Fortunately or unfortunately, that wasn't quite the case because many mathematicians worked technology out and they worked for different types of root systems, also the solutions out, but not for this type of root system. In fact, there's very few work. They usually stopped when they got to these type of so-called BC root systems. In fact, there's one notable exception. Didina actually had worked a long time ago on these root systems. So we couldn't really just copy the formulas from the book, but the technology is there. So for you, it's probably good news, because it means instead of just producing now a long list of formulas for conformal blocks, I'll actually show you a little bit of the technology that is used to produce these formulas, and that might be also interesting in other contexts. So here is so the basis story. Of course, I will be somewhat brief on that. So one thing is, of course, when we want to control this ZZ bar dependence of the conformal blocks, right? These are function of Z and Z bar of the cross ratios, and we have to understand the ZZ bar dependence quite explicitly. For instance, in order to compute these overlap that we want to compute between T-channel and S-channel blocks to construct the crossing kernel. So, and so as a consequence of integrability, these conformal blocks in a d-dimensional conformal field theory, they actually satisfy a Knitzig-Samolotchikov-like equation, okay? Very much like, well, you have that in 2 dimensions, but this is actually a statement about d-dimensional conformal blocks, okay? And that follows more or less directly from these Dunkel operators, and you can work out the connection explicitly. So there's a matrix connection in this case, which basically was worked out by Matsu and Chiretnik in independent papers. So which tells you that, so there's a flat connection, okay? So for the simplest case of the Peschel-Teller problem, this flat connection is actually just a 2x2 matrix connection, and there's only one variable z around. And so the conformal block essentially is just the component. So when you have this flat connection, you integrate the flat connection. I guess here everybody knows these kind of things. And so then you just pick one of these components. In fact, in this case, it's just the sum of the 2 components, and that's going to be your conformal block. Okay, so that's the claim. And so also for this case that is relevant for d-dimensional conformal field theories, you can work out this matrix connection. In this case, it's an 8x8 matrix connection, has 10 different singularities, and all the residues can be computed. So you see in this case, I didn't really point this out, but it's not so important what the precise form is. But here in this BC1, the Peschel-Teller case, you have just one variable. So this variable here is related to the x variable by this map. And then there's this connection as singularities in 0, plus, minus 1. and the residues are some matrices that depend on the parameters of the problem. Okay, some particular matrix connection. And you can, of course, integrate that, and what you get out of it more or less for free is that you can write all these conformal partial waves as iterated integrals. Okay, that also applies for d-dimensional, but the formula, of course, looks a slightly bit more complicated. But it's super explicit. I could have written the 8x8 matrix connection on a slide. It's just not very illuminating, but it looks similar to it. So it's totally explicit. In fact, one can do actually better. There's, in fact, a beautiful theory how to integrate such KZ connections. And this is now getting closer to sort of the real groups of theory of hypergeometric and modern theory of spatial functions. So it turns out that you can, when you have such a connection, there's a strategy where you kind of embed it into a Gauss-Manning connection on Grassmannians. And if you succeed to do that, you get your integral formula more or less for free. Okay? So it turns out in this case for the Purcell-Teller problem, the Gauss-Manning connection, the relevant one, so the Grassmannian is basically a subset sitting in GR26, parameterized by one parameter y. So this is a particular one parameter family of hyperplanes. And on this family, you have this Gauss-Manning connection is a 4x4 matrix connection, which you can work out as standard formulas. And then you can show that these Knitzig-Schaum logic of connection that I wrote on the previous transparency, that can be embedded as a 2x2 matrix connection. So you can find explicitly an embedding of these 2x2 matrix connection into this 4x4 matrix connection. And once you have that, you can write down integral formulas. And when you apply this theory to this case of this Purcell-Teller problem, you get the following integral formula here. Looks like that, involving the parameters a and b and h. And you can check that this is really an integral representation of the hypergeometric function 2f1 with these parameters, and this is indeed the conformal block. So you get the right formula for the conformal block as an application of this theory. Okay? Yeah. Yeah, so there's different representations of 2f1, integral representations. And when you apply this theory, you actually get this funny integral representation that you may not recognize immediately as a correct integral representation of 2f1. It's not the minimal choice, but it's one correct integral formula for 2f1. And that's the one that comes out from this theory. Okay? So, but in some sense, it's as good as the one that you know. I mean, it has only one integration, has a bunch of factors, has a few more than you're used to, but that doesn't really make it less convenient. Sorry?
What are the two critical points? Usually it's like 0, 1, or...
So yeah, so the reason is indeed that for this funny integral representation is that we use a different variable, right? In the KZ connection, the typical variable was this y. And when you think about it, sorry, actually, I actually didn't write an argument here. So this 2f1 here on this side is actually an argument z, okay? But here on the other side, I use y, and then if you follow the slides, you will see that there's a complicated nonlinear integral transformation. That's kind of the reason. The KZ connection lived in a different variable, okay? But it's still a true equation. I mean, okay, it's true once I put the z in, okay, and it can be checked. So if you're interested in this type of technology, which is really fun, there's a fantastic book of Aomoto that explains all these things, and I think it's very useful. So yeah. So in fact, once you do this, in fact, that's just work in principle. You can repeat that presumably for the BC2 case, for this case that is relevant for conformal blocks. We believe you get a similar integral equation with a few more integrations for the blocks in a d-dimensional conformal field theory. Once you have this formula, you can actually use it directly to compute the crossing kernel, okay, as a function of the delta and L. Now, I don't know, maybe very briefly, there's a lot more integrability in this problem. So once you have computed the crossing kernel, it's a function of delta of the conformal weights and of L, and you might be interested in understanding what the dependence is on delta and L. Okay? In particular, if you want to think of it as an integral transform, you might want to know what the asymptotic behavior is in terms of delta of the conformal weights. And And so integrability it's much deeper in this problem than you might first think. In fact, there's also an integrable system that controls the dependence on delta and L in this story. And again, when you have a free particle, you know the wave functions are e to the I kx. And so the x dependence and the p dependence are more or less symmetric. Okay, so you know also have a differential operator that controls the k dependence of waves. And similar in this case, for the Calogero-Sutherland problem, you get these eigenfunctions. They are eigenfunctions, of course, functions of the conformal cross ratios, and they depend on the eigenvalues on delta and L. But there is sort of an integrable system that controls the dependence on delta and L, and this is actually the Roisner-Schneider model. And that's also integrable, and you have, again, a whole lot of technology to find solutions and control explicitly the dependence of these objects in terms of delta and L. So, yeah, so maybe I leave it at that. There is many other aspects of this integrable story. So there's, in fact, many other parameters on this side of the integrable systems that one can introduce. This is part of a kind of a network of integrable theories, and they all play a certain role in this story. But at least I hope I convinced you that with this amount of integrability, you can actually get useful formulas, integral formulas for the quantities of interest. Now, good. So are there any questions on this? Yeah.
Is there any meaning of more like n particles?
Not that I know of. There is other systems of similar type which have a meaning, but just putting n particle, I don't know of a particular application in terms of a bootstrap. I'll get back to that. Good. So I'm already coming to the end, so I promised I would talk a little bit about future directions or further directions. So one thing you might say, so I've tried to convince you, first of all, that there's this equivalence between these two problems, the construction of conformal partial waves, the building blocks of a conformal bootstrap, and these Calogero-Sutherland wave functions. And I hope to convince you that there is actually really a use of the integrability in this story in terms of getting explicit formulas for the quantities. So one of the further directions is you might wonder whether this is kind of an accident somehow, because, I mean, okay, I didn't introduce any supersymmetry. I only looked at scalar fields in the theory. So it turns out that there's actually sort of a more general underpinning of this story, which explains, first of all, why there's integrability in this problem, and also shows that this extends to a wide class of similar setups. So what we studied quite explicitly in the last few months was the case of where we replaced these four fields by spin fields that carry spin, not just scalar operators. And in that case, based on some kind of group theoretic harmonic analysis description of the problem, we actually constructed an algorithm that allows you to systematically construct this quantum mechanics description, and it becomes some sort of matrix version, the matrix quantum mechanics, where you have these Calogero-Sutherland potentials, but they're no longer scalar, but they're usually matrix Calogero-Sutherland models. For those of you who are familiar with some matrix Calogero-Sutherland, there's a notion of spin Calogero-Sutherland. It doesn't seem to be that this is identical. So it's matrix Calogero-Sutherland, but not the standard spin Calogero-Sutherland model. So we've worked this out in some examples. In particular, Genya has done some very beautiful work to show, to compute this for non-trivial spinning blocks in 3 dimensions. He found very beautiful formula and also showed that it agrees with some expression that for the Casimir operator, the Casimir equation that appeared in the paper last year. And after proper variable transformation, one can actually bring it in a much nicer form compared to, I mean, this original paper, and in particular into this Calogero-Sutherland form. So, so there, this general strategy that I described here or sketched here applies to many other cases. You can do spinning blocks in other dimensions. This is not restricted to 3 dimensions. You can, of course, also introduce supersymmetry and do the same thing for supersymmetric blocks, in particular when you have non-BPS external states. And also there's problems of the type that many people here also like, where you have boundaries or defects, and then also you have building sort of the kinematic building blocks of that story. For all these things, you can adapt this technology and derive similar types of quantum mechanics problems. So that partly answers Kolya's question. I mean, I think there is a wider class of this type of quantum mechanics problems that appears in the context, but for this simple n-particle extension of the BC2 problem, I don't have an application. But there's many other systems that have. And by general arguments, which are, okay, still need to be worked out, I guess, most of these things should be integrable, and one should be able to develop a solution theory more or less along the lines of what I sketched very briefly in the third part of the talk. Now, I think, like working out, I mean, again, I remind that this, what I've just described in the last last half an hour, was concerned with the kinematics of the story. I think it's actually worthwhile to kind of finally close this chapter on the kinematics. I hope I convinced you that this is mathematically controllable, but it has to be just worked out. So I think there's still some stuff about conformal and superconformal groups that just needs to be worked out, and I think the technology is there, and this should be done. Of course, I would also want to end with reminding you that, of course, the ultimate goal is to then turn back to this equation that so what I've just now described here was basically the strategy to construct this kernel function, okay, and to control all its properties. And as I told you, this is just this is a kernel function, and then sort of solving for dynamics means solving these this integral equation. And well, we have some ideas on how this is done. But of course, this requires a lot further research. One thing that might be interesting in this context is that in 2 dimensions, of course, we have lots of solutions of this equation. And in the kinematics, the dimension, remember the dimension d was just the coupling constant and the potential. Okay, so, and the coupling constant and the potential is a continuous parameter. Okay, so that, in fact, should be very important in terms of generating new solutions in d dimensions. So it's important for us, but I think it's also important for Volodya, because he was a bit worried about the fate of this conference series after going from 4 to 3 to 2 dimensions in terms of broadness and depth. But so you see, we skipped over lots of dimensions, and I'm sure there is some appropriate metric in the real numbers that shows that all these other dimensions are as broad and deep, or broader and deeper, and so there's a lot of room for future work. So I hope some of this will feature also in Paris. Okay. Good.
Is there also a story from Virasoro blocks?
Sorry?
Virasoro blocks.
What's the question? Virasoro blocks like here, yeah?
Can you, is there an integrable model that takes
Yeah, so this is not the story here, but I mean, this was actually very nice. I mean, there's some very nice work of Didina and Vincent Pasquier and Raul Santachiara that discusses Virasoro blocks and the connection. There's some relation with AN Calogero-Sutherland models in this case. And in this case, N really has something to do with the number of punctures inserted. Okay, so in 2 dimensions, it's a little different because every time you put an extra point, you get one more parameter. Okay, when you're in D dimensions, of course, every time you have a new field, you put in D new parameters generically, unless you have a very small number of points. But so in 2 dimensions, there's a direct relation between the number of points and the number of particles in this quantum mechanics problems. Yeah, so this is a beautiful paper of a few years back.
More questions?
Can you write a closed form expression for conformal blocks
dimensions?
So, you see, I mean, closed form means a nice manageable integral formula that you can use to derive more expressions and read off asymptotics and things like this. Yeah. So, as I said, I probably should have pointed that out. So, in order not to disappoint you too much, disappoint you now, when I ask you what this C is, I cannot write it down at this point. Okay, but it's being worked on, and I think it's a matter of a few weeks to write down nice integral formulas for this.
If I remember it correctly, then even dimensions there is some.
Yeah. So in even dimensions, you can see that's a very good. So in even dimensions, there is a formula, and when people say there is a formula, then these are formulas where you can write it in terms of one variable hypergeometric functions. Okay. So this is very, very exceptional. So there's some cases where it's actually possible to write it in terms of one variable hypergeometric functions. But from what I explained to you more or less, you can see that this is just totally exceptional. This is just an accident somehow. And you can actually see it in the Calogero-Sutherland model. You see, we, like at least some of these examples. Sorry, that goes the wrong direction. Oh, sorry, it's unfortunately very far back. No, this was here. So you see, for instance, in 2 dimensions, of course, epsilon is 0. And so this is a non-interacting quantum mechanics problem. But when you go to 4 dimension, epsilon is 2, and it's also 0 in this. So there's also a case of a non-interacting problem. And so again, it can be written in terms of one variable hypergeometric function because it just factors into two non-interacting things. And the only coupling between left and right movers comes sort of from this gauge transformation here. And that agrees, in fact, with the formula that people wrote down. Okay, so the 6-dimensional case is a little harder to argue, but it also comes from symmetries of the problem. So it's a complete accident that you can write it in terms of one variable hypergeometric function. If your question is, can you write a formula in terms of one variable hypergeometric function, the answer is clearly no. But you can write it in terms of 2 variable hypergeometric functions of a very beautiful type that are actually very well controlled and understood. Okay, because in this huge zoo of hypergeometric functions of multiple variables, there are some that are much better than others. And this belongs to that class. So when you have defects, okay, I didn't really describe the setup too well, but it turns out, maybe one version I can describe here. So it turns out that you can model these conformal blocks, and in fact that is at the origin of this story, the ones that I described here, by looking at the following double coset. You take the conformal group, and this is a subgroup generated by dilations and rotations. And you divide this from the left and the right. You divide the conformal group by this thing, and you can check that this is actually 2-dimensional space. And with the appropriate coordinates, I mean, you can see that the blocks, I mean, the functions, I mean, eigenfunctions of Laplacian become these conformal blocks, okay? So when you want to describe defects, you just have to change this coset description, okay? So you have, maybe on one side, you have still this dilation times rotation. On the other side, you have the conformal group that preserves your defect, things of this type. So you get very similar setups, and you can follow general recipes to work out these quantum mechanics problems.